Welcome. In this mini lecture, we're going to talk about equivalence classes and partitions. If you recall, in our last lesson, we talked about equivalence relations and determined that equivalence relations were relations that were reflexive, symmetric, and transitive. So, we're going to begin by looking at a proposition. And our proposition states that the relation congruence modulo n on the set of integers is an equivalence relation. This is a really useful fact, particularly there's a lot of things that come up in abstract algebra that use this. So we're going to look at first proving that this relation is an equivalence relation. So note that A will be related to B if and only if A is congruent to B mod n. So let's begin our proof. And we'll go ahead and let A, B, and C be integers. And now we're going to prove each of the properties, starting with reflexive. So, if we let A be an integer, and we will first note that 0 is equal to n times 0. Thus, we can say that n divides 0, and more importantly, n divides a minus a. Thus, by the definition of congruence modulo n, we know that a must be congruent to a mod n. Hence, A is related to A for every A in our set. So we have shown that our relation is in fact reflexive. Moving on to symmetric, we start by supposing that A is related to B. Thus, A is congruent to B mod n, which in turn, by the definition of congruence modulo n, we have that n divides a minus b, which in turn means we may write a minus b equals nk for some integer k. Now, b minus a would be equal to n times a minus k. Again, we just multiplied the previous equation by a negative 1, which gives us that b minus a is equal to n times a negative k. Thus, n has to divide b minus a, and further, b is congruent to a mod n by the definition of divides and then by the definition of congruence modulo n. Hence, b is related to a, and we know our relation is symmetric. Lastly, transitive. So in this case, we suppose that A is related to B and B is related to C. So that tells us that A is congruent to B mod n, which in turn gives us that n divides A minus B, and that in turn tells us that we have A minus B is equal to nk. Similarly, B is congruent to C mod n, which in turn tells us that n divides B minus C, which in turn tells us that B minus C is equal to NP. And these, of course, are for some K and P, which are integers. Now, if we take those two terms and add them together, A minus B plus B minus C, well, that would have to be NK plus NP. On the left, we'll be left with A minus C, and on the right, we'll have an N times a K plus P, which in turn, this tells us that N has to divide A minus C, which in turn tells us that A is congruent to C mod N, and hence we get that A is related to C. Since our relation is reflexive, symmetric, and now transitive, we know that it is in fact an equivalence relation. So we've completed our proof. We do our happy dance. So now that we know how to prove things are equivalence relations, we're interested in going one step further. This brings us to the definition of an equivalence class. So if we have an equivalence relation R on a set A, we can take any element A in that set and determine the equivalence class of A, and that's the set of all elements that are related to A. And we use this notation of square brackets to denote the equivalence class. So let's look at an example. If you remember, in our last mini lecture, we proved that the relation R on Z, defined by x is related to y if and only if 3x minus 7y is even. So we know that it was an equivalence, or we know that it was an equivalence relation. So now we're interested in determining what are the equivalence classes. So in doing so, we're going to just choose some element. Let's say 0. So what we're interested in is all the elements, all the integers, such that x is related to 0. So if we do a little bit of thinking off to the side here, that means that 3x minus 7 times 0 is even. That's what we need to figure out. Which x's make that a true statement? Well, because it's an equivalence relation, we know that 0 is definitely related to itself. So what about 1? Is 1 related to 0? No, because 3 times 1 would be 3, and that would be odd. But when we choose 2, 3 times 2 would be 6, minus 0, would be even. As we continue testing numbers, we would see that 4, 6, all the even numbers seem to be working. And in fact, if we start testing negative values, we find that all the negative even integers also work. So 0 is one equivalence class. Well, what's the next integer we can think of that didn't occur in the previous set? Well, how about 1? So again, I want all of the integers such that x is related to 1. So certainly 1 is in there. 2 was in the previous set, and in fact, let's pause a moment and remind ourselves, what is it that we're interested in? We need 3x minus 7 times 1 to be even. So if I plug in 1, that's certainly going to work. 2 is not going to work, but 3 does work, because 3 times 3 is 9 minus 7 leaves us with 2. Similarly, 5, 7, and it would seem that all of the odd integers are going to work. And in fact, they will. So you might ask yourself, well, what about 2 or 3 or 4? What other integers might give us an equivalence class? So if we pick something else, I don't know, say 5, well, what's going to be in there? We put in 5 because we know that's going to work. And again, if you're thinking about what would this mean, we would need 3x minus 7 times 5 to be even. We're going to find that 3 is going to work, 1's going to work, 7 is going to work. And again, we're just going to get all the odd integers. So what this tells us is that the equivalence class of 1 and the equivalence class of 5 are the same. So when writing this, we generally take the smallest positive value and we just consider the equivalence class 1. But it would be equivalent to the equivalence class of 3, of 5, of 7, but we're just going to represent it with 1. And this brings us to our next definition. A partition of a set A is a set of non-empty subsets of A, such that the union of all the subsets equals A, and the intersection of any two different subsets is the empty set. So, if we think back to our previous example, and we will look at that, the equivalence classes formed a partition of the integers. All of the even integers were in the equivalence class of 0, and all of the odd integers were in the equivalence class of 1. Together, the equivalence class of 0 and 1, the union makes up all of the integers, but the intersection of those two sets is empty. Hence, the equivalence classes of a relation form a partition. And that's where theorems 11.1 and 11.2 come in. If we have an equivalence relation on a set, we know that the equivalence classes of A and B are the same if and only if A is related to B. Also, if R is an equivalence relation on our set, the set of equivalence classes forms a partition of A. So that means that the union of those equivalence classes has to be the same as the set A, but the intersection of any two equivalence classes is the empty set. The proofs of both of these theorems are nice element-chasing arguments. You should read them in the book, and they could also make a very nice quiz question. So you should make sure that you read them and understand them. That's all for now. Thanks for listening. Have a great day.